IcVce graph from a BJT. So let's take a look at this graph. All right, so I've got on my right hand side, I've got my BJT hooked up from my collector, base, and emitter, right? And on my left hand side, I've got my Ic-Vce graph. So first of all, you have to be, again, very familiar with the BJT. Now coming in here, I've got my IB. Coming down here, I've got my IC. And this is your VCE. Yeah. So another thing that you have to be very familiar with is the concept of beta. Okay, beta is found by taking the ratio of IC over IB. Okay, so these are some of the things that you need a little bit of background information to help you understand the Ic-Vce graph. So first of all, let's assume that the beta value is 100. Okay, so if we have a beta value of 100, that means for every IB that we have, IC is 100 times that of IB. And we can see this from the Ic-Vce graph. So if I have 100 microampere for your IB, so if I have 100 microampere going in here, I should have a corresponding value of 10 milliampere. It's 100 times more. Yeah. So likewise, if I increase my IB, to 200, my IC coming down will be 20, and so on and so forth. So depending on what the base current value you use, you will have a corresponding collector current flowing down here. All right. So that's one thing, how you read why I have so many lines. I'm putting many different scenarios. For each IB value you use, you have the corresponding IC value flowing down. Next, you'll notice that if I do not have an IB, if I do not have a base current, I will not have a collector current. And anything below that is 0. So we call this the cut-off region. This is your cut-off region. Yeah. And you'll notice that this area also does not affect anything. This is my saturation region. Yeah, this is my saturation region. So what's happening here? Yeah, so you'll notice that by right, if I increase my voltage at VC and therefore VCE increases, if I increase my VCE, this is my VCE value, let's say 1, 2, 3, 4, so on and so forth, by right. So by right, once you increase the VCE, if you increase the VCE, you should have an increase. You should have an increase of your IC flowing down, right? This is according to Ohm's law, right? So with a bigger voltage here, you should get a bigger current flowing down here. But we see that that is not the case. When we increase the VCE here, when we increase the VCE, IC doesn't seem to increase. It remains steady at 10 milliamperes. Maybe there's a slight upward slope, but that's about it. So the thing here is you have to interpret this graph is that once I have selected a base current, let's say 100 microamps, it will more or less give you 10 milliamps in the collector current. Even though I can increase my VCE, the collector current more or less stays constant. Yeah, so that's one thing, one information that I can get from this graph. Yeah. So another information that I can get is that when will I hit saturation regions? So let's choose a different colored pen to illustrate this. Right, so let's say I want to use a 0.5 VCE. So let's say my VCE value here is 0.5 volts. Now, if I am using whatever IB value I have, I find that I hit saturation very fast. Yeah. So if I want to use if I want to get a value greater than 20 milliamps for my IC, perhaps 0.5 is not a good value because I will hit saturation even before I can go past 20 milliamps. I won't be able to go anywhere past this point. Okay, I won't be able to go anywhere past 25 or so, whatever that is, whatever value that is. So if I want to have a greater IC current at saturation, perhaps maybe I can increase my VCE value. Yeah, so that's how I interpret this graph here. Okay, so a couple of things. One, know that this is the cutoff region. Any value below IB equals to 0, it is cut off. It's in an off state. And any value that lands over here, any value that lands in this area is in the saturation state. Okay, so that's one thing that you have to know. Another thing that you have to know about this is the load line. Now, this gets a little bit complicated, but first let's find out how a load line comes about. I'm going to follow this branch of line here. I'm going to start off with VCC, and if VCC, if I take away your ICRL, and I take away my VCE by Kirchhoff's voltage law, this will give me 0 volts. Yeah. So if my VCE is 0, if my VCE is 0, my IC equals VCC over RL. Yeah, and if my IC is 0, it means my VCE equals, when this whole thing becomes 0, VCE becomes VCC. So with these 2 points, I can plot when VC when IC equals to 0, when IC equals to 0, this is actually my VCC value. And when VCE is 0, when VCE is 0, depending on the load resistance, I can have another point somewhere maybe here. Yeah. So if I plot a line, between my 2 points, this is called your DC load line. Yeah, based on this point and this point. Now, the whole idea behind this is that I want to find my operating point, what they call a quiescent point. And ideally, the quiescent point should be somewhere in the center, because if I have an input here, and I'm talking about using a BJT as a amplifier, the output, what I want at the output, yeah, is a very nice amplified signal like this. So that's ideally, the input is a nice sine wave and the output gives you a very nice amplified sine wave. So that's the ideal situation. Yeah. So ideally we want to have somewhere in the middle here. Why do we say we want it to be somewhere there? Because if I were to draw this as my maximum and this as my minimum, right? It shouldn't go below saturation. If I were to choose somewhere along this point, for example, yeah, it could be a possibility whereby the wave might get cut off if you choose a point too close to the VCC point, because, well, you can't create energy, you can't get a voltage greater than VCC. And likewise, if I choose a point too close to the saturation point, same thing, I'm going to have a region that is cut off. Yeah, so I don't want a distorted output signal. I do not want anything cut off here. I do not want anything cut off there. This I do not want. So what I do want is somewhere in the center where the output gives a very nice sine wave like this. So I do not risk a distorted cutoff here, and neither do I risk a distorted cutoff there. Okay, so this is the whole idea behind why I want to find out a load line. And if I have the load line over here like this, ideally the operating point I want is somewhere in the center to prevent any distortion at the ends. Now, I also do not want a load line that is like this. I do not want that. I also do not want a load line that is like this. Yeah, because that will kind of mess with where your operating point is. So to find out what is the proper load line, you have to bear in mind what is your load resistance, and that will determine your IC point here, your y-axis point here. Okay, so I hope I've kind of tried to attempt to explain how to read your Ic-Vce graph. And yeah, if you got any questions, you can email me or ask me those questions in class.